Through the use of this activity, we'll be working on determining if a number is rational or irrational. Take a look at the word rational. It has the word ratio inside of it. So that's supposed to remind us that a rational number can be written as a ratio or a fraction. Look at the word irrational. IR means not, and then we have this word ratio. So an irrational number cannot be written as a ratio, or we could say cannot be written as a fraction. We're going to use this chart as a reference. And let's take a look at the first example. 0.1 repeating, so that's 0.11111. And we're asked first in the first column, the decimal is terminating, repeating, or has no pattern. Which of those choices? Well, we would say that this has a repeating pattern. It's a repeating decimal because the decimal goes on forever and there's a repeating pattern. Next, we determine if this number is rational or irrational. Well, every repeating decimal is a rational number because repeating decimals can be changed to fractions. And then in the last column, what we need to do is write this as a fraction. It says if the number is rational, record the number as a fraction. So it was rational. So I'm going to go ahead and write this as a fraction. Remember, with repeating decimals, what we can do is we can use the 9 rule. So if the pattern is one number long, like it is in this case, you put the pattern at the top, and then we're going to place it over 1, 9. So we use the 9 rule or the algorithm when we are converting a repeating decimal to a fraction. Let's look at example 2, 0.1. It looks similar to number 1, but 0.1 ends. It terminates. It doesn't keep going on forever. So this is called a terminating decimal. And all terminating decimals are rational numbers because they can be written as fractions. Now, to change a terminating decimal to a fraction, you have to use place value. So the 1 is in the 10ths place. So we place the 1 over 10 to change this decimal to a fraction. Let's look at example 3, the square root of 36. So let's look back at our chart. 36 is a perfect square. So if you take the square root of 36, we'll get an integer, 6 and negative 6. So we're going to say that it has a terminating decimal. If I wrote it, it would look like this, 6, or you could say 6.0. The decimal ends. And then we need to determine if it's rational or irrational. Well, terminating and repeating decimals can both be changed to fractions, so that's a rational number. And then we need to write this as a fraction. So let me go over to my drawing tool. It's either 6 over 1 or negative 6 over 1, because the square root of 36 is equal to positive or negative 6. Let's move on to number 4, the square root of 2. We'll reference our chart. If you look at the perfect squares, 2 is between 1 and 4. 1 is a perfect square, 4 is a perfect square, but 2 is not a perfect square. No integer multiplied by itself gives you 2. So 2 is actually an irrational number. I'm going to fill that in first. It's irrational because we know that if we type this into a calculator, the square root of 2, since 2 is a non-perfect square, we're going to get a decimal that has no pattern and goes on forever. So let me go back to the graphic organizer and I'm going to type that this is a number 3, has no pattern and never ends. So I'm going to type it in, has no pattern, the decimal has no pattern, and never ends. Let's see if this will fit. And it does. And I'd like for us to actually write repeating, terminating, has no pattern, never ends, because I think that helps us to remember it as we're just first now starting to work with rational and irrational numbers and these types of decimal expansions. Okay, the square root of 2, well, it wasn't rational, so we can't record it as a fraction, so we leave this part blank. You could put not applicable if you want to. Okay, moving on to pi. Well, pi is equal to 3.1415926 blah, 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 blah. It's an irrational number. And then that means we also know that it has the decimal has no pattern, so there's no repeating pattern, and never ends. You could say goes on forever. And this part is not applicable. Since it was an irrational number, we can't write it as a fraction, so we don't have any fraction to put in that column. All right, moving on. Number 6. Is the decimal expansion terminating, repeating, or has no pattern? Well, cubed root of 60, I need to look at my perfect cubes. So if I look at my perfect cubes, 60 falls between 27 and 64. 60 is not a perfect cube. So if you take the cubed root of a non-perfect cube, let me show you what happens. Oops, wrong tab. The cubed root, let me clear this. The cubed root of 60, since 60 is not a perfect cube, we're going to get a decimal that goes on forever and has no pattern. If you took the cubed root of a perfect cube, for example, let's say you take the cube root of 64, 64 is a perfect cube, you'll get an integer. So it's only when you take the cube root of a number that is a non-perfect cube, that's when you get an irrational number. All right, so going down to this, the cube root of 60, this is an irrational number, and it has, the decimal has no pattern and never ends. And we can't write it as a fraction. All right, the cubed root of 27. The hope is that you already have your perfect cubes and your perfect squares memorized. Personally, I wouldn't go back and look at the chart because I would just remember my perfect cubes and perfect squares, but this is here in case you don't have these memorized yet. So 27 is a perfect cube. So when you take the cubed root of 27, you'll get an integer, 3. So this is we have a terminating decimal because it would be 3.0, and that would be a rational number. All terminating decimals, numbers with terminating decimals can be written as a fraction. And then I'll grab my drawing tool, and this would be equal to 3 over 1. There's actually only one answer to a cubed root. Remember, there are 2 answers to a square root, except for special cases like the square root of 0. Square root of 0 is just 0. Okay, pi divided by 2. So this is something else I want to show you. If you take pi and you divide it by 2, it's still going to be irrational. I didn't mean to do that. Let me erase that. So I'm going to type that into the calculator. So I type in pi divided by, oops, I didn't mean to write pi, 1 pi divided by 2. And this number has a decimal expansion that has no pattern, and you'll just have to trust me that it really does go on forever. So if you divide pi by a number or you multiply pi by a number, it's still going to be irrational. The only time it would not be irrational is if you took, let's say you took pi and divided it by pi. Well, pi divided by pi is 1. Anything divided by itself is 1. But if you divide, you take pi and divide it by 9, it's going to be irrational. If you take pi and multiply it by 20, it's going to be irrational. Basically, if you divide it or multiply it by a number, it still should be irrational. So let me move back to the text box. pi divided by 2 is going to have a decimal expansion that has no pattern and never ends. It's an irrational number. And since it's an irrational number, we cannot write it as a fraction. So there's nothing to put in that column. All right, moving on to number 9. Number 9, negative 0.7. Well, this is a terminating decimal. There's no line above the 7. So this decimal expansion is terminating. Terminating means that it ends. A terminating decimal ends. And all terminating decimals are rational numbers because terminating decimals can be turned into fractions using place value. So this is the 10th place. So I would put 7 over 10, and it's a negative 7/10. Now all the problems I put on this activity page, they can't be reduced because I was trying to save you a little bit of time since this is a lot to take in. So don't worry about reducing fractions. Number 10, going back to the text box, 0.77777. That's a repeating pattern. It goes on forever. It has a pattern. Repeating decimals can be changed into fractions. So this is a rational number. And for repeating decimals, what you do to change it to a fraction is you use the 9 rule. So if there's one number in the pattern, which is true in this case, you're going to put it over 1 9. So negative 0.7 is equal to negative 7/9. Let me fix that 7. All right, number 11. 700. Well, 700 is the same as 700.0. So this has a terminating decimal. Numbers with terminating decimals are rational. They can be written as a fraction. And to write this as a fraction, we would just write 700 over 1. You can change any integer to a fraction by putting it over 1. All right, negative 4 times pi. Let's apply what I talked about earlier. Let's multiply negative 4 times pi. And we get a decimal expansion that goes on forever and has no pattern. So we would say that the decimal has no pattern, so it's not repeating, and it never ends. So that decimal expansion goes on forever. And this is an irrational number. And you can't write this as a fraction since it is irrational. So I'm going to put not applicable. Number 13. Now this looks like a pretty long number, but it actually terminates. So this is a terminating decimal. Terminating decimal, and all terminating decimals are rational numbers. They can be written as a fraction. And to write them as a fraction, we use place value. So let me count it out. Tenths, hundredths, thousandths, 10,000ths, 100,000ths. So I put 100,000 in the denominator. And then in the numerator, I put 17,033. And normally we would check this, but 17,033 is a prime number. I know that because I made that problem, so you can't reduce that. Number 14, the square root of 256. Hopefully you already remember that 256 is a perfect square. It results from multiplying 16 times 16, or negative 16 times negative 16. So this is going to have a decimal expansion that is terminating. Think about it. 16.0 or negative 16.0, the decimal ends. So that means that this is a rational number. And if I were to write this as a fraction, I would write 16 over 1, that's one answer option, or negative 16 over 1. Those are both answers to the square root of 256. And then finally, number 15, negative 0.8383838383. So this is a repeating decimal because it has a repeating pattern. Repeating decimals go on forever. And all repeating decimals can be changed to fractions, so that's a rational number. And we can use the 9 rule to convert this to a fraction. So there are two numbers in this pattern, 8 and 3, which means that we need to put this over 2 9s. So when you're doing your work on your own for these examples, remember that when you do change some of these to fractions, you don't have to worry about reducing. I made sure you didn't have to reduce. And go ahead and do your best. Use the examples that we completed together to help you.